What's up, guys? This is Chris McCormick. If you've been following the NLP news, then you probably saw that after BERT came out at the end of 2018 with its really impressive benchmark results, we've seen a number of other models come out that are kind of like variations on BERT that have stolen the top spot in the benchmarks, like XLNet and Roberta. And then you've also seen probably that people have been trying to make BERT smaller, right? Because BERT is a really big model and it's very slow to fine tune as well as to use for inferencing. So it'd be really nice if we could, have a model that is a lot smaller and lighter, but mostly as accurate as the original BERT. So there's been work in that direction as well. And at the end of 2019, another model came out named Albert. It stands for a light BERT. And it's the work of a team at Google Research and Toyota. And if you read some of the hype around this model, like in Google's blog post here on Albert, you'll see a couple things. You'll see, that it took the top spot on the benchmarks. That's really cool. And then you'll also see in here a lot of mentions of this parameter reduction, 89% parameter reduction. So Albert base, 89% fewer parameters, but still achieves respectable performance. So it looks like Albert has done it all. It's got the highest accuracy as well as the smallest footprint, the lightest weight model. So I think it'd be kind of natural to think like, okay, so BERT is, outdated. It was cool when it came out, but clearly Albert has just surpassed it in every way here. The reality, though, is that if your intent is to take BERT and fine tune it for some kind of task that you want to apply it to, then you're going to find that Albert base isn't any faster to train or any more accurate necessarily than the BERT base model. So clearly there's some kind of disconnect here between, what you'd kind of glean from the hype versus, what the reality is. And in this video, I'm going to explain that discrepancy and also share some of our experiences with it. It was interesting that, not only did it not improve things, but for Nick and I, it was a big headache even getting it to work. So I'll kind of share that experience as well. So there's a couple points I want to share about Albert that I think will clear up this confusion for us. And the first is that, in spite of its name, a light BERT, Albert was never actually intended to be a lightweight BERT. So if you look at a model like DistilBERT, they actually set out to create a version of BERT that would be faster to fine-tune, faster to inference, but still retain as much of the original accuracy of BERT as possible. So Albert is really about going bigger. They kind of allude to this in the next sentence here. So they talk about the big parameter reduction, but then they say this parameter size reduction provides the opportunity to scale up. And that's really what it's about. So those impressive benchmark numbers they got are with this Albert extra large configuration. And it uses a hidden size of 4096. So the hidden size is the length of those embeddings that are passed between the 12 layers of the BERT architecture. The original BERT was used 768 features. So Albert extra large is 4096. And the number of parameters in the model grows quadratically with this length. And the reason for that is that a lot of the matrices are square. So I'll show you some of the math here. So for BERT base, the original, it used a size of 768, and the self-attention matrices, for instance, are square. So they're 768 by 768. So if you grow this number, then it grows quadratically. So with Albert extra large, it's 4096. So there's actually 200 million weights per encoder. Compared to 7.1 for the original BERT, so or the original BERT base. So it's 30 times larger. And if what you're interested in is fine-tuning Albert and inferencing it in some kind of application setting, then really it has 2.4 billion weights in it. So it's not, Albert extra large is not lightweight at all. It's probably one of the biggest, if not the biggest, models on those leaderboards. I'd be curious to know if there's anyone that's kind of gone bigger than this. Now that number is not what they report in their paper. So if you go in the paper and look at table 2, their Albert extra large configuration has 12 hidden layers, which is interesting. They kind of found that 12 layers is enough. Doing more layers didn't actually help. And they've got this really large hidden size of 4096. And they're reporting that their model only has 235 million parameters. So there's a couple things here. The first is that they did this interesting trick with the embeddings. And the way they use the term embeddings here is to refer specifically to that vocabulary of 30,000 words and subwords and the vectors that represent those words. So those are the embeddings. And rather than have an embedding size that is the same as the vectors that are passed between the encoder layers, they use a much shorter embedding length of 128. And then they just have a projection matrix that blows that small embedding back up to a length of 4096. So kind of a cool technique. It saves about 120 million parameters compared to if they were to use embedding size 4096. So that's a lot, but we're still like more than 2 billion parameters away from this number. So by far the biggest parameter savings comes from this concept right here, parameter sharing. And parameter sharing is really fascinating. They offer some insight in the paper into why it works. Really, I think when you see it, it seems like it should break the model. And the fact that it doesn't break it, and in fact actually enables the model to perform really well on these benchmarks, raises some really interesting questions about what these deep neural networks are actually doing. So let me show you what parameter sharing means in this context. Now, in BERT, we've got 12 encoder layers, and they're all identical in terms of their structure, but each one has a unique set of weights. So I've colored each one, kind of a different shade of green to show that there's 12 of them, but each one has its own set of parameters. So in Albert, they still have the 12 encoder layers, but the parameters used by each encoder are identical. So they're all using the same set of weights. So really, Albert just consists of one encoder that you apply 12 times to those embeddings. So if you're surprised that this works, then I'm right there with you. I feel like the way that deep neural networks are often explained, especially in computer vision, is that the initial layers are looking at these kind of more basic features, and then as you move deeper into the network, they're looking at more abstract features. And what Albert seems to be telling us is that really it's like, no, it's the same thing at every layer. You just need to apply this transformation 12 times. So I'd say the one piece that does match our intuition maybe is that on its own, this parameter sharing technique does hurt the model. So if you were to take BERT base with the hidden size of 768 and share the parameters across all 12 layers, then it doesn't perform as well as BERT with unique weights in all 12 layers. Rather, the point seems to be that it enables scaling. So if you take BERT and use that same hidden size of 4096, it doesn't actually work. The accuracy on the benchmarks goes down. So there's something about this parameter sharing concept that enables BERT to learn more and go farther. So if we go back to the confusion around the number of parameters in the model, it can really be explained by just adding the qualifier here that this is the number of unique parameters in the model. So Albert only has, the extra large version only has one encoder's worth of weights plus the embedding layer. So it's only got 235 million unique parameters. And that has some nice properties. It means that, if each of these parameters is 4 bytes, then this is, just under a gigabyte of either, disk space or RAM to hold it. So that's nice. But, if we're talking about like applying the model to a task, if we're running inferencing, then you still have to apply the encoder layer 12 times. So if you're looking at the parameter count in terms of the inferencing cost, then 2.4 billion is the right number. And the same goes for fine tuning. Even though there's only one encoder, you still have to run backprop on 2.4 billion weights. So that's where the confusion comes in, I think. All right, so hopefully I've answered the question for you in the title of this video. It seems to me like most people probably don't want to mess with Albert given the huge scale of the model. But maybe I'm wrong. Maybe people are more willing to play with those larger sizes than I think. So if you know of an example, I'd love to hear about it. And to wrap things up, I wanted to just share my experience and my experience with Nick in getting Albert working in our notebook. But before I do that, you should know that there's more to Albert than just the parameter sharing. We've covered kind of these first two, but there's actually a total of 6 changes that the authors of Albert made to BERT. So the first 2 are parameter sharing and that trick with the embeddings matrix that we saw. They also defined this new training task called sentence order prediction. And then these 3, they pulled from other projects, other research that's been done and incorporated into Albert. So if you want to learn more about all of these things, Nick and I have published an ebook on this. He helped me a lot with the research and wrote a couple of the sections, so thank you, Nick. It's currently sitting at about 25 pages. I think we're still wrapping up a couple of the sections this week, but it covers all 6 of those topics. And with it, I've included a copy of our fine-tuning for sentence classification notebook. And we've just made the changes necessary to have it run with Albert. We'll show you some of the hyperparameter choices that they made for Albert. And then for fun, I've also got a copy of it where we use the extra large variant of Albert. So that's actually running right now. So you get to see how that turned out. And then I did something new with this ebook. I did like a read through of the Albert paper and just kind of marked it up with emphasis where I thought things were important or clarifications that were helpful to me, as well as just some questions like areas of that I still need to understand better. So I'll make sure that's included with the book as well. So I'll drop the link for this ebook down in the description of the video. So give it a look, and I hope you find it really valuable. If you're interested in trying out Albert, the Hugging Face Transformers library has nice support for it. It's just kind of a drop-in replacement for BERT. Nick and I had a frustrating time getting it working though, and I thought I'd just kind of like share that story real fast. So we swapped in Albert for BERT on a sentence classification task, COLA benchmark. And the training loss looks pretty good, except that if you look at the y-axis, it's not really going down. It's going from 0.62 to 0.58. And for comparison, here's kind of what BERT base looks like. It goes from 0.5 down to below 0.15. So, it performed really poorly. We tried tweaking the hyperparameters. We thought, maybe like the hyperparameter choices are different for Albert. Maybe they're really important, and that's why it's not working for us. but just as bad here. Didn't even break 0.6 this time. And then we also kind of looked at the script in the Albert GitHub repo and saw that, it looked like maybe they were training it for more epochs than we were. So we thought, hey, maybe that would fix it. Maybe it just needs to be trained longer. Tried 20 epochs and still kind of the same result. Ended up in the same spot. So finally, we had the thought to try switching which version of the model we were using. So if you look at the Albert GitHub repo, you'll see that they've published a version 2 of the model where they've changed the training regimen a little bit, and it gets better results on the benchmarks. So, might as well use the better one, right? So we started with Albert base v2. When we switched to Albert base v1, all of a sudden it worked. So if we ever figure out, what we were doing wrong or what's wrong with v2, I'll post that in the description of the comments or something like that. In the meantime, if you're thinking about using Albert, maybe be wary of version 2 of the model. There might be something wrong there. So just a sort of like anecdotal evidence of some of the things that we've talked about here. I applied both BERT and Albert base to this Wikipedia data set. The Wikipedia dataset has 69,000 training comments in it, and Albert was a little bit faster. They both took about 25 minutes per training epoch, but Albert was 11 seconds faster on average. And if I had to guess, I'd say that's probably due to the smaller embedding matrix size in Albert. And then in terms of inferencing, running on the test set, here, let's say this is 69,000 training comments. Evaluating the test set, this is 23,000 test comments. So inferencing on 23,000 took about 3 minutes, and it was actually slower for Albert. And again, if I had to guess, I'd say that's once again due to the embedding matrix, because now they've added an additional step. Whereas before you just looked up the embedding vector, now you look up the embedding vector, multiply it against this projection matrix to bring it up to the larger size, and then send it through the network. So basically the same training speed, a little slower test evaluation speed. In terms of accuracy, it did do better, but I think to really benchmark this, you'd want to like average more runs and account for any sort of like variance in the model. And either way, it's not enough of a gap there to be really impressive. So a lot of headache to get it working, and then not great results in the end. So again, if you're just playing around with BERT, then Albert may not be worth trying out, unless that maybe small memory footprint is really interesting to you, or maybe if you're willing to go to the larger model sizes. But maybe most significantly, I'm really interested to see what the NLP community does with this parameter sharing insight. It seems really surprising and interesting. So we'll have to see where it goes. Thanks, guys.